Mr. Chairman, ladies and gentlemen, good morning. I'm very glad to have this opportunity to attend the conference. My name is Haonan. I'm from Yunnan University. The topic of my presentation is design of interplanetary observation terminal based on a programmable system on chip. My presentation will include these four parts. First, the background of our research. Second, the specific we will do. Third, experimental results. Last, some conclusions we have got. Firstly, I would like to introduce the background of our research. Interplanetary scintillation refers to the phenomenon that electromagnetic waves emitted from radio sources outside the solar system are scattered by the solar wind when they pass through the interplanetary space of the solar system, causing random fluctuations in electromagnetic intensity. With the continuous development of human space exploration and aerospace technology, solar wind activity monitoring and space weather forecasting are becoming more and more important. The drastic change in the solar wind can cause magnetic storms, power transmission facilities into malfunctions, interfere with the ground shortwave communications, satellite communications, and even threaten the safety of spacecraft and astronauts. Therefore, it is of great significance to predict solar wind activity by monitoring IPS signals. The 40-meter radio telescope at the Yunnan Astronomical Observatory in China is one of the important observation equipment for radio astronomy signals in China. Compared to Qingyang 25-meter, Miyun 50-meter, and fast, Yunnan Astronomical Observatory 40-meter radio telescope is located in the southwest low latitude and can observe many radio sources that cannot be observed by other radio telescopes. According to the experience of scientists in IPS observations, when the observation frequency of the radio telescopes is low, the radio source information is more abundant, such as 327 MHz, therefore improving the receiving equipment of the 40-meter radio telescope near the 300 MHz frequency band of Yunnan Observatory for IPS observation is of great significance to fill the gap in its IPS signal observation capability. Secondly, I will introduce our specific work for you. Now we can see system overall structure block diagram. Firstly, the system uses a low noise amplifier to amplify the weak radio signal received by the 40-meter radio telescope. Then, the analog downconversion mode is used to downconvert the received 327 MHz analog signal to obtain a 10 MHz signal. Then the intermediate frequency amplifier is used to amplify IF signal. The digital is input to PL side of APSoC through AD9648. Real-time power calculation and superposition of signal are carried out in PL, and then the superposition power data is avenged and stored in system memory through XI4 bus for reading by PS side. When the data is read, PS side transmits it to the LabVIEW host computer software in the form of gigabit Ethernet UDP protocol for real-time display and store. In addition, the system can also configure the gain channel and clamping coefficient of the AD9648 in the hardware receiver through serial communication in the host computer application and issue control commands. Next, I will introduce the design of the PL side of the system. In order to achieve the high-speed acquisition and processing of IPS signals and ensure the stability of the system, the basic framework of IPS signal processing is constructed in the PL side of APSoC. As a characteristic, time scale of IPS signal changes from 0.1 second to 10 seconds in order to improve the system time resolution. The PL side is used to calculate the power of signal sampling points within 10 milliseconds and calculate the average. Because the date interval between sample points is very small, reaching nanosecond level, the process of power calculation and superposition needs hardware acceleration at PL side. Then the power data is mapped to the memory address through XI4 bus for subsequent reading by PS side. The data processing part, mass IP, consists of power calculation mode, power superposition mode, and the data to XI IP to compute the calculation and superposition of the IPS signal power, and transmit the data to the PS side for subsequent processing, since dB is commonly used as a unit in engineering. Log operation should be performed on the raw date, since the power value to be sent is the average power value within 10 milliseconds. The amount of the data is small, and a large number of LUTs will be consumed if the log operation is implemented using the PL side in order to save logic results. On PL side, log operation is carried out on PS side. Next, I will introduce the design of PS side of the system and the LabVIEW host computer. In addition to logarithm taking and data packing operations, in order to achieve flexible parameters control, that is, to control the sample channel gain, and the clumping coefficient parameters of AD9648 through serial port, and to realize the function of calling other IP cores and controlling gigabit Ethernet for data communication, it is necessary to build the PSI operation program in the Cortex-A ARM processor. The main program flow of PSI is shown in Figure 4. The program flowchart of the LabVIEW host computer application is shown in Figure 5. The main functions include serial port communication and UDP communication between the host computer and APSoC. Second function is display and storage of IPS power data. The LabVIEW host computer interface is shown in the figure below. Okay, now we move to the part of experiment. Firstly, we tested the function of UDP and central port, and they all work well. Secondly, we tested time resolution of the system, as can be seen from Figure 8. When the signal power alternates from minus 10 dBm to minus 40 dBm, the power value will change in real time with the change of the input signal. When the time of a single step scan in 3 seconds, the system output data points are 300 points. So the system time resolution can be calculated as 10 milliseconds. After rapid measurements using the above method, the system time resolution is 10 milliseconds, so it meets the design requirements. Thirdly, we tested stability of the system. As can be seen from Figure 9a, when the signal power is weak, the continuous observation results basically pretend a straight line. After calculation, the signal power fluctuation is about plus or minus 1 dBm, indicating that the system has good test accuracy and stability and meets the design requirements. Finally, we tested PSI resource usage and power consumption. As can be seen from Table 1, BROM and BUFG are the most used resources on PSI of the system, accounting for 17.5% and 21.88% of the total resources respectively. DSP is the least usage resource, and only 1% of the total resources are used, indicating that the system has a large amount of resource margin and good scalability. And the power analysis tool in Vivaldo was used to evaluate the power consumption of the pure side of the system. The power consumption was 1.955 volt in actual operation, which met the design requirements of low power consumption of the system. Now, we come to the last part, conclusion. In this paper, we proposed an IPS observation system based on Xilinx Zinc 7000 APSoC. The system takes XC7Z020 CLG4841 as the core. Realize the real-time processing and transmission of IPS power signal by means of hardware and software cooperation, and realize a good human-computer interaction interface based on LabVIEW. Experiments show that the system has high integration, high time resolution, and good stability. The work in this paper has laid a technical foundation for the 40-meter radio telescope of Yunnan Astronomical Observatory to carry out IPS observation and has certain application value. Next, we will consider integrating the post-processing of IPS signals into APSoC to improve system performance. That's all my presentation. Here is my email address. If you have any questions, please feel free to contact me. That's all. Thank you.